This video in my Color and Light series is about highlights, and please remember to subscribe. Highlights are direct reflections of the light source. If the source is a window, we see that window on the surface as shown in this mug. If the source is the sun, then we see a reflection of the sun on the water. In calm water, you would only see one reflection, but in this image, each wavelet reflects light to us like many tiny mirrors, elongating the glare. The highlights tell us how smooth the surfaces are. Think of light as a cone enveloping one side of a ball, like a baseball mitt. So here we have a sphere and a cone of light enveloping it. The axis of the cone tells us the direction of the light. The light is tangent to the sphere, hitting it at two single points, marking the edges of the terminator that divide the light area from the shade. Now, some people call the shade the form or core shadow, but I find these terms confusing, so I'm just going to call it the shade. These tangent light rays also hit the two edges of the cast shadow. And the highlight right here lies along the central light ray, closer to the edge of the ball than to the terminator. To understand highlights, you need to look at the relationship between the sphere, the light source, and the viewer's eye. The highlight is the exact spot where the ray hits the sphere, then travels directly to the eye, so it's the lightest part of the sphere. The highlight moves not only with the light source, but also with the viewer. And it's the only element in shading that moves with the viewer. So here again we have the sphere and the light source, but this time we have two viewers. This is the one we talked about last time, and now viewer 2 sees a light ray that comes in this direction. As the eye moves further left, the highlight moves toward the terminator, and once the light ray is tangent to the sphere, the highlight is gone. Now let's position ourselves where these eyes are located. So the person in this position would see mainly a light area with the highlight in the middle, closer to the edge than to the terminator. The person over here would see mainly shade and a sliver of light with the highlight in the middle, again closer to the edge than the terminator. But the terminator doesn't change. We are just walking around this sphere looking at it from different angles. What does change is the highlight. Here, it's very far from the terminator, and here, it's very close to the terminator. To find the highlight, draw tangent light rays from the ends of the terminator to the edges of the cast shadow. The highlight is along the center of the cone of light, closer to the edge of the ball than to the terminator. Notice that this edge is darker than the rest of the light area. Highlights can never be on the edge because light hitting the edge goes back to the source and we don't see it, making this area dark. The highlight becomes more distinct as the surface gets smoother and as light intensity increases. So this ball has a shiny surface in intense light, so its highlight is distinct. This ball is semi-glossy with less intense light, so its highlight is fainter. This tennis ball has a matte surface, so the highlight and the light area merge together because we only see distinct highlights on shiny surfaces. The intense light causes reflected light in the back of the ball. It also removes many of the halftones, so the light area is just one value and the terminator is very distinct. And that makes the ball look less spherical than the other balls. Catchlights are highlights on the eye since the eyeball is shiny, and they reflect the light source like this window here. They're better seen on animals with dark eyes, but don't put the highlight in the middle because it may make them look evil. In my drawing here, the highlight is whiter than the white of the eye because the highlight is a reflection of the light source, and the eyeball should get darker as it goes toward the edges like any sphere. The tiny little lines here, and you can see them better over here, are shadows of the eyelashes. And in the middle is what the eye actually sees, and usually includes the viewer. Over here, you can see a window and a window seat, and in this eye, you can see sky and clouds. Highlights on shiny cylinders follow the sides. So here the terminator is near these red dots, and over here, even though I've moved to the left, the terminator is still near the red dots. But the highlight here is near these openings, and over here it's further to the left of the openings. But in both cases, the highlight is nearly in the middle of the light area. I have a summary here of the video, which you can read on your own. But what I want to talk about is, why is the light area darker than the highlight? The highlight is the one spot where the light hits the sphere and comes directly to our eye. But what about this spot right here? Light will hit that spot, and most of it will go off in a different direction, and only a little of it will be deflected to our eye. So this area will look darker. And what happens is that the very bright highlight gets gradually darker as we move away from it. In these images, the sun is behind my right shoulder. Here I'm in front of the pole, and here I'm more to the left. The terminator hasn't changed position, and you'll just have to take my word on that. But the highlight has. In this case, it's nearly in the center of the light area, but always closer to the edge than the terminator. And over here, it's much closer to the edge. So the highlight changes position because I moved. Now, highlights shouldn't be distinct white spots because it's not realistic. And as you can see here, they gradate from the highlight to the light area. And a white spot would appear to be in front of and separate from the object. So I want to quote Paul Schristic, who said, "The gradation toward light is what makes the highlight effective. In the middle of a quiet musical passage, a cymbal crash would be noise. But as a final note in a crescendo, it's exciting and stirring." My next video will be about light direction, and I just want to remind you that my Kindle version is only $5.